Hello there, and welcome to the Scientist Sleepy. Tonight, we embark on a gentle exploration of the very origins of matter itself, a calm lecture on how the fundamental building blocks of our universe, the atoms, came to be. We will journey back to the dawn of time, to the fiery heart of stars, and the explosive deaths of celestial giants, to uncover the profound and often surprising story of atomic creation. Prepare for a quiet investigation into the cosmic forces that shaped everything you see and everything you are. Please allow yourself to settle in. Find a comfortable position, let your body soften, and release any tension you may be holding. If it feels right for you, consider giving this video a gentle like and perhaps subscribing to the Scientist Sleepy. Subscribing ensures you won't miss our future explorations into the quiet wonders of the cosmos, and it helps us continue to create this peaceful haven for curious minds. And if you feel so inclined, sharing a thought or a question in the comments below, even a simple observation, is always welcome. Now, let us begin our drift. The universe's first whisper, hydrogen atoms formed. Imagine, if you will, a time before time. A moment so profound, so primal, that our very concept of before begins to dissolve. This is the era of the Big Bang, not an explosion asterisk in asterisk space, but the explosive expansion asterisk of asterisk space itself. In those first infinitesimal fractions of a second, the universe was an unimaginably hot, dense, and energetic soup of fundamental particles. As this nascent cosmos expanded, it began to cool. This cooling was not a passive process. It was the crucial phase where the very building blocks of matter, the atoms, began to coalesce. The simplest and most abundant element, hydrogen, was the first to truly come into being. Its creation is a testament to the fundamental forces of nature playing out on the grandest possible stage. In the immediate aftermath of the Big Bang, conditions were so extreme that even protons and neutrons, the particles that would eventually form the nuclei of atoms, were in a constant state of flux. They were either being formed or annihilated in a delicate cosmic balance. As the universe expanded and cooled, this balance began to shift. The energy levels dropped, making it less likely for newly formed protons and neutrons to be torn apart. Protons, which are simply the nuclei of hydrogen atoms, were the most stable and readily formed particles. They emerged from the primordial energy field, a testament to the universe's inherent drive towards structure. Then came the crucial step, the formation of atomic nuclei. For hydrogen, this is remarkably simple. A single proton is the nucleus of a hydrogen atom. So, as the universe cooled below a critical temperature, protons could persist without immediate annihilation. They became the bedrock of all future atomic creation. However, the universe wasn't quite ready for fully formed atoms just yet. For a while longer, the universe remained a plasma, a hot, ionized gas where electrons, stripped from their nuclei by the intense heat, zipped around independently. The universe was still too hot for electrons to bind with protons to form neutral hydrogen atoms. It was about 380,000 years after the Big Bang, a period known as recombination, when the universe finally cooled enough for a profound transformation. At this point, the temperature had dropped to around 3,000 Kelvin. This was the magic number. Electrons, now moving at slower speeds, could be captured by the positively charged protons. This capture wasn't a violent event, but a gentle binding, an embrace dictated by the electromagnetic force. When a free electron met a free proton, they formed a neutral hydrogen atom. This was the universe's first true whisper of structure, its first stable, organized entity. It was a moment of profound significance, marking the transition from a formless, energetic plasma to a universe composed of actual atoms. These hydrogen atoms, vast in number, began to fill the expanding cosmos. The immense gravitational pull of these newly formed hydrogen atoms then began to assert itself. Over millions of years, these atoms, scattered across the vastness, started to clump together. They were drawn into denser regions, forming the first nebulae, the great clouds of gas and dust that would become the birthplaces of stars. So, the creation of hydrogen atoms was not a single, instantaneous event, but a gradual process driven by the cooling and expansion of the universe. It began with the emergence of protons from the primordial energy of the Big Bang, and culminated in the gentle capture of electrons, forming the neutral atoms that would eventually gather to ignite the first stars. It's a story of immense scale, of fundamental forces, and of the universe's patient unfolding, beginning with the simplest of structures. And so, in the quiet vastness, the first atoms, like nascent thoughts, began to drift, carrying the potential for all that was to come. Stardust's alchemical dance, helium's birth in the early universe. In the earliest moments of existence, long before stars ignited their brilliant fires, a profound transformation occurred. The universe, a swirling, searing plasma of fundamental particles, began its first, most fundamental act of creation. Imagine the cosmos, a mere fraction of a second old, impossibly hot and dense, a boundless ocean of protons and neutrons, electrons and photons, all in a state of chaotic, energetic flux. This was the primordial soup, the very crucible from which the first atoms, beyond the simplest hydrogen, would emerge. As the universe expanded, it cooled. This cooling was not a gentle descent, but a dramatic slowing of unimaginable energy. Think of it like a rapidly expanding gas, losing its heat as it spreads. This cooling allowed for the fundamental forces of nature to assert their influence, and for particles to begin to bind. The dominant force at this stage, for the formation of atomic nuclei, was the strong nuclear force, a powerful, short-range attraction that could overcome the electrostatic repulsion between positively charged protons. The conditions were perfect for a process known as Big Bang nucleosynthesis. This wasn't the slow, deliberate fusion that happens within stars over billions of years. This was a rapid, intense period of nuclear reactions that occurred within the first few minutes after the Big Bang. Protons, the nuclei of hydrogen atoms, were the most abundant building blocks. When two protons collided with sufficient energy, they could fuse. However, this fusion was not a simple direct path to helium. The first step involved the fusion of two protons. This was a rare event, as protons repel each other strongly. But when it happened, one of the protons could transform into a neutron through a process involving the weak nuclear force, releasing a positron and a neutrino. This created a deuterium nucleus, an isotope of hydrogen consisting of one proton and one neutron. Deuterium is a crucial stepping stone in the creation of helium. Once deuterium nuclei were formed, they could readily fuse with other particles. A deuterium nucleus could fuse with another proton to form a helium-3 nucleus, which consists of two protons and one neutron. This reaction also released a high-energy photon, a gamma ray. Alternatively, two deuterium nuclei could fuse. This could result in the formation of a helium-4 nucleus, two protons and two neutrons, releasing a neutron and a lot of energy. Or it could form a helium-3 nucleus and a proton. The most stable and abundant form of helium produced during this epoch was helium-4. Its nucleus, with two protons and two neutrons, is remarkably stable. The formation of helium-4 was a significant step because it marked the creation of the first nucleus that was not simply a single proton. It was the first heavier element in the grand scheme of cosmic origins. The process didn't stop cleanly with helium. Some deuterium nuclei also fused with helium-3 nuclei to produce helium-4 and a stray proton. And some helium-4 nuclei could fuse with protons to form lithium-7 nuclei, a slightly heavier element, though this reaction was less efficient and occurred in smaller quantities. Crucially, this period of Big Bang nucleosynthesis was finite. As the universe continued to expand and cool, the density of particles decreased and the energies of the particles dropped. The rapid, high-energy collisions necessary for fusion became increasingly rare. Within about 20 minutes after the Big Bang, the window of opportunity for this rapid nucleosynthesis closed. The universe became too diffuse and too cool for further significant fusion to occur. What was left was a cosmic composition dominated by hydrogen, about 75% of the mass, and helium, about 25% of the mass, with trace amounts of lithium. This ratio of hydrogen to helium, established in the first few minutes of the universe's existence, is a profound piece of evidence supporting the Big Bang model. Astronomers observe this very same ratio in the oldest stars and gas clouds, a testament to the universe's initial fiery birth. The helium we find today, in the air we breathe, in the stars that light our night sky, and even in the inert gas used in balloons, is largely a direct descendant of that initial, explosive alchemical dance. And so, in the universe's nascent moments, a fleeting, fiery ballet of fusion etched the first elements into the fabric of space-time, a testament to the power of cosmic cooling and the fundamental forces that shape reality. Cosmic furnaces ignite, the creation of heavier elements in stars. Deep within the vast, silent expanse of the cosmos, a profound and majestic process unfolds, a slow, deliberate alchemical transformation that has shaped the very fabric of our existence. We speak now of the stellar furnaces, the incandescent hearts of stars, where the universe's most fundamental building blocks are not merely present, but actively forged. Imagine, if you will, the immense gravitational pressure at the core of a star, a force so powerful it compresses matter to unimaginable densities. It is within this crucible that the magic truly begins. Stars, in their infancy, are primarily composed of the lightest elements, predominantly hydrogen and helium, the direct descendants of the Big Bang. But as a star matures, its core becomes a reactor, a place where the fundamental forces of nature conspire to fuse these simple elements into something far more complex, far more substantial. This process is known as nuclear fusion. At the immense temperatures and pressures found at a star's core, hydrogen nuclei, which are essentially single protons, are forced together with such violence that they overcome their natural electrostatic repulsion. Through a series of intricate steps, 4 hydrogen nuclei can combine to form a single helium nucleus. This is the primary energy source for most stars, including our own sun. The energy released in this fusion process is what makes stars shine, bathing their surrounding systems in light and warmth. But the story does not end with helium. As a star exhausts its hydrogen supply in its core, gravity begins to win the battle. The core contracts and heats up even further. If the star is massive enough, these increased temperatures and pressures become sufficient to initiate the fusion of helium nuclei. 3 helium nuclei can fuse to form a carbon nucleus, and in more massive stars, this carbon can then fuse with other helium nuclei to create oxygen. This process continues, step by step, with each stage requiring higher temperatures and pressures than the last. Helium fuses into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and so on, creating a layered structure within the star, much like an onion, with heavier elements being formed closer to the core. Each fusion stage releases energy, but also produces heavier, more stable nuclei. This is the cosmic alchemy, the stellar forging of elements. The stars are not just distant lights. They are the factories of the universe, meticulously crafting the elements that will eventually form planets, moons, and indeed, all life. The very atoms that make up your body, the carbon in your cells, the oxygen you breathe, the iron in your blood, were all born in the fiery hearts of stars that lived and died long before our solar system even existed. This ongoing creation within stars is a testament to the universe's capacity for transformation, a constant process of building complexity from simplicity. The forces at play are immense, the temperatures staggering, and the timescale measured in millions, even billions of years. Yet, the result is a universe rich with the diversity of elements, a cosmic tapestry woven from the dust of stellar furnaces. The brilliance of a star is not just light. It is the visible manifestation of the profound creation of matter itself, the ongoing genesis of heavier elements from the primordial simplicity of hydrogen and helium. It is a process that connects us directly to the most ancient and powerful forces in the cosmos, a reminder that we are, quite literally, stardust. This stellar nucleosynthesis, as scientists call it, is the fundamental engine that enriches the universe with the raw materials necessary for the formation of planets and the emergence of life. Without these stellar furnaces, the universe would be a far simpler, and perhaps lifeless place, composed only of the primordial hydrogen and helium left over from the Big Bang. The stars, in their magnificent, fiery existence, are the architects of elemental diversity, the grand sculptors of matter. They are the cosmic kitchens where the fundamental ingredients for everything we know are meticulously prepared, atom by atom, through an enduring cycle of cosmic creation. The stars, in their fiery core, are the universe's patient alchemists, transforming the simple into the sublime, giving birth to the very elements that compose our world and ourselves. Stellar nurseries bloom, nebulae as the cradles of atomic creation. Imagine, if you will, vast, ethereal clouds stretching across unimaginable distances in the cosmic expanse. These are nebulae, not merely pretty celestial sights, but the very nurseries where stars, and consequently the atoms that compose them, are born. They are immense reservoirs of gas, primarily hydrogen and helium, the primordial elements forged in the initial moments of the universe, along with trace amounts of dust, tiny grains of heavier elements scattered by the explosive deaths of previous generations of stars. These nebulae are not static. They are dynamic, swirling, and ever-changing environments, sculpted by gravity, stellar winds, and supernova shockwaves. Within these grand cosmic clouds, the magic of atomic creation, or rather, the aggregation and concentration of existing atoms into new stellar forms, begins. Gravity, the fundamental force that pulls all matter together, is the silent architect here. In denser regions of a nebula, where gas and dust particles are more tightly packed, gravity's pull becomes stronger. These denser pockets start to attract more surrounding material, slowly but surely growing larger and more massive. As a pocket of gas and dust grows, its gravitational influence increases, creating a feedback loop that draws in even more matter. This process is incredibly slow, unfolding over millions of years. The initial atoms of hydrogen and helium, scattered thinly throughout the nebula, begin to coalesce. As more atoms gather, the cloud begins to collapse under its own weight. The material spins faster as it contracts, forming a flattened disk around a central, increasingly dense core. This core is the nascent protostar. The pressure and temperature within this collapsing core begin to rise dramatically. The atoms are being squeezed together with immense force, their kinetic energy increasing with every collision. This is where the true transformation into a star and the subsequent creation of heavier atoms truly begins. The nebula, once a diffuse and seemingly chaotic expanse, becomes a structured birthplace. The outer regions of the nebula may continue to form new stars, or perhaps the material will coalesce into planets and other celestial bodies orbiting the newly formed star. The dust within the nebula, those microscopic remnants of stellar alchemy from eons past, plays a crucial role. These dust grains, composed of silicates, carbon compounds, and even tiny metallic particles, act as nucleation sites, providing surfaces upon which gas atoms can condense and clump together. Without this dust, the formation of molecules and ultimately the dense cores needed for star birth would be far less efficient. So these nebulae are not just collections of atoms. They are the grand stages upon which the universe rehearses its ongoing symphony of creation. They are the cosmic wombs, nurturing the seeds of future stars, and in doing so, continuing the grand process of atomic evolution that began with the Big Bang. The light we see from distant nebulae is the light of newly forming stars, or the light of existing stars illuminating the gas and dust, a testament to the continuous cycle of matter and energy in the cosmos. Within the nebulae, atoms gather, not to be born anew, but to be reborn as stars, continuing the universe's grand, patient design. The fusion's fiery heart, how stars forge elements from lighter ones. Deep within the incandescent core of stars, a process of unimaginable power and profound significance unfolds: nuclear fusion. It is here, under pressures so immense they defy earthly comprehension and temperatures reaching millions of degrees Celsius, that the very building blocks of the universe are reconfigured. Stars, in essence, are cosmic alchemists, transforming the simplest elements into a dazzling array of others, a celestial forge that paints the cosmos with the materials necessary for planets, life, and all the wonders we observe. The most fundamental of these stellar furnaces is the fusion of hydrogen, the universe's most abundant element, into helium. Imagine billions upon billions of hydrogen nuclei, the protons at the heart of hydrogen atoms, hurtling towards each other at incredible speeds. These nuclei, normally repelling one another due to their positive electrical charges, are forced into proximity by the crushing gravitational embrace of the star. When they collide with sufficient energy, the strong nuclear force, a fundamental interaction far more potent than the electromagnetic repulsion, takes over. This force binds them together, overcoming the electrostatic barrier and initiating the fusion process. In the Sun, the primary mechanism for this transformation is the proton-proton chain. This is not a single, instantaneous event, but a series of delicate steps. First, two protons fuse to form a deuterium nucleus, which is an isotope of hydrogen with one proton and one neutron. This process also releases a positron, a particle of antimatter similar to an electron but with a positive charge, and a neutrino, a nearly massless particle that interacts very weakly with matter, carrying away a significant portion of the energy released. The deuterium nucleus then fuses with another proton to create a helium-3 nucleus, an isotope of helium with two protons and one neutron, also releasing a gamma-ray photon, a form of high-energy light. Finally, two helium-3 nuclei collide and fuse to form a stable helium-4 nucleus, which consists of two protons and two neutrons. And in the process, two free protons are ejected, ready to begin the cycle anew. The net result of this proton-proton chain is the conversion of 4 hydrogen nuclei into one helium-4 nucleus. But the energy released in this transformation is truly staggering. According to Einstein's famous equation, E equals mc2, a tiny amount of mass is converted into a tremendous amount of energy. This energy, primarily in the form of photons and neutrinos, is what powers the star, causing it to shine and radiate heat across the vastness of space. This radiant energy slowly makes its way from the star's core, through its radiative zone and convective zone, eventually escaping from the star's surface as light and heat that can travel for light years. It is this gentle, yet inexhaustible, outpouring of energy that sustains life on planets like Earth, warming our world and enabling the complex chemistry that underpins our existence. As a star ages and its core becomes increasingly filled with helium, the temperature and pressure can rise further, allowing for the fusion of helium into heavier elements. This process, known as the triple alpha process, involves the fusion of 3 helium nuclei, each composed of 2 protons and 2 neutrons, to form a carbon-12 nucleus. This is a more complex and energetically demanding process than hydrogen fusion, requiring even higher temperatures. Carbon is a crucial element, forming the backbone of organic molecules and thus, life as we know it. From carbon, further fusion reactions can occur, leading to the creation of oxygen, nitrogen, and other elements. These heavier elements are forged in successive stages within the star, each requiring progressively higher temperatures and pressures. For instance, carbon can fuse with helium to produce oxygen, and oxygen can fuse with helium to create neon. This cascade of fusion reactions continues, building up heavier and heavier nuclei within the star's core, until elements like silicon and sulfur are formed. However, this process of stellar nucleosynthesis, as it is called, has its limits. The fusion of elements up to iron-56 releases energy. Iron is a particularly stable nucleus, meaning that it requires a significant input of energy to break apart or to fuse with other nuclei to form heavier elements. Therefore, once a star's core is dominated by iron, the fusion process that generates energy ceases. The star can no longer support itself against its own immense gravity, leading to a catastrophic collapse and, in the case of massive stars, a spectacular supernova explosion, which we will explore in later chapters. The fusion within stars is not merely a process of element creation. It is the fundamental engine of cosmic evolution, the source of the light that illuminates galaxies, and the raw materials that seed the formation of new stars and planets. Every atom in our bodies, from the carbon in our bones to the oxygen we breathe, carries within it the echoes of these stellar furnaces, a testament to the profound interconnectedness of all matter in the universe. The heart of a star beats with the rhythm of creation, turning simple whispers of hydrogen into the vibrant symphony of heavier elements that paint the cosmos. The iron limit: why stars cannot create elements beyond iron through fusion. Deep within the hearts of stars, a magnificent process unfolds: nuclear fusion. It is here, under unimaginable pressure and heat, that lighter atomic nuclei are coaxed together, merging to form heavier ones, releasing torrents of energy that illuminate the cosmos. This stellar alchemy is the primary engine for the creation of most elements we find in the universe, from the ubiquitous hydrogen and helium forged in the Big Bang, to the carbon, oxygen, and nitrogen that form the very basis of life. For much of a star's life, this fusion process is a steady, predictable dance, governed by the fundamental forces of nature. As hydrogen fuses into helium, then helium into carbon, and so on up the periodic table, each step releases energy. This energy release is crucial. It creates an outward pressure that counteracts the star's immense gravitational pull, maintaining a delicate equilibrium. However, this harmonious process encounters a profound boundary, a cosmic roadblock, at the element iron. Iron, with its atomic number of 26, represents a unique turning point in stellar nucleosynthesis. The reason for this limit lies in the very nature of nuclear binding energy. When atomic nuclei fuse, energy is released if the resulting nucleus is more tightly bound than the original nuclei. Conversely, Energy is required to fuse nuclei if the resulting nucleus is less tightly bound. For elements lighter than iron, fusion generally leads to more tightly bound nuclei, and thus, energy is released. This released energy is what powers stars and allows them to shine. However, when we consider the fusion of elements that would result in iron, a different energetic landscape emerges. Iron 56, the most common isotope of iron, possesses one of the highest binding energies per nucleon of any element. This means that the nucleons, protons, and neutrons within an iron nucleus are held together with an exceptionally strong force. Consequently, fusing lighter elements to create iron releases a significant amount of energy. But here's the critical point. Fusing iron with other nuclei, or fusing iron with itself, does not result in a more tightly bound nucleus. Instead, the resulting nuclei are either less tightly bound or the energy input required to force them together exceeds any energy that might be released. In essence, iron is the most energetically stable element in terms of nuclear fusion. Once a star's core accumulates a significant amount of iron, the fusion process that has sustained it begins to falter. The energy-producing fusion reactions cease, and the outward pressure that supported the star against its own gravity begins to diminish. Without this outward push, gravity takes over with a vengeance. The iron core, no longer supported by fusion, collapses catastrophically. This rapid collapse triggers a violent rebound, a supernova explosion, which is the very mechanism responsible for creating elements heavier than iron. These heavier elements are not formed through sustained fusion within the star's core, but rather through explosive processes involving rapid neutron capture. So, while stars are cosmic alchemists, their creative power through fusion reaches its zenith at iron, a point where the energy balance shifts, marking the end of one era of creation and the dramatic beginning of another. The iron limit is not a failure of stellar processes, but rather a fundamental consequence of the laws of physics that govern the universe's atomic architecture, guiding the cosmic evolution of matter. Like the steady hum of a star's heart, the iron limit reminds us that even in creation's grandest displays, there are fundamental balances that shape the universe's unfolding story. Supernova's explosive artistry, the violent birth of elements heavier than iron. When stars, much more massive than our own sun, reach the end of their fiery lives, they do not simply fade away. Instead, they undergo a cataclysmic event of unimaginable power, a supernova. This colossal explosion is not just a spectacular end. It is a cosmic forge of unparalleled intensity, where the very elements that make up our world and ourselves are violently born. For stars, fusion is the primary engine of creation, but this process has a limit. Within the immense pressures and temperatures of a star's core, lighter elements like hydrogen and helium are fused into progressively heavier ones. This continues, stage by stage, until the star's core is predominantly iron. Iron is a critical turning point because fusing iron nuclei consumes energy rather than releasing it. This means that once a star's core is saturated with iron, its internal energy source is effectively shut off. Without the outward pressure generated by fusion to counteract the relentless inward pull of gravity, the star's core collapses catastrophically. In a mere fraction of a second, the core shrinks from thousands of kilometers across to just a few tens of kilometers. This rapid collapse triggers a massive rebound shockwave that blasts outward through the star's outer layers, tearing the star apart in a supernova. It is in the searing, fleeting moments of this explosion that the universe's most profound alchemy takes place. The shockwave not only disperses the star's existing material, but also creates an environment of extreme neutron density and temperature. Here, a process known as the R process, for rapid neutron capture, can occur. Newly formed nuclei are bombarded by an overwhelming flux of neutrons, capturing them at an astonishing rate. These neutron-rich isotopes are highly unstable and quickly undergo beta decay, transforming neutrons into protons and thus creating new, heavier elements. This is how elements like gold, platinum, uranium, and many others, heavier than iron, are synthesized. Without these violent stellar explosions, the universe would be a much simpler, and indeed a much less interesting place, devoid of the very building blocks that allow for the complexity of planets, life, and our own consciousness. The elements we are made of, from the calcium in our bones to the iron in our blood, have, in large part, been forged in the heart of long-dead stars and scattered across the cosmos by their spectacular demise. The remnants of stellar death are the genesis of earthly wonder. Neutron stars' dense embrace, a cosmic forge for the heaviest elements. Imagine, if you will, the remnants of stars far more massive than our Sun, collapsing under their own immense gravity, not into the gentle white dwarfs we discussed, but into something far more extreme, far more dense. These are neutron stars, the collapsed cores of supernovae, packing the mass of our Sun into a sphere no larger than a small city. Within their incredibly powerful gravitational fields, and under conditions of unimaginable pressure, a unique cosmic alchemy takes place, a forge where the very heaviest elements are brought into existence. When a massive star explodes as a supernova, it doesn't just scatter lighter elements. It creates an environment so energetic, so saturated with free neutrons, that it allows for the creation of elements heavier than iron, elements that stellar fusion alone cannot produce. This process is known as the rapid neutron capture process, or the R process. In the heart of a supernova explosion, or perhaps even more effectively in the cataclysmic merger of two neutron stars, an extraordinary abundance of neutrons is unleashed. These neutrons, with no electrical charge, can readily penetrate the nuclei of existing atoms, even those that are already quite heavy. They slam into these nuclei at incredible speeds, adding themselves to the core, increasing the number of neutrons significantly. However, a nucleus with too many neutrons relative to its protons becomes unstable. It undergoes a process called beta decay, where a neutron transforms into a proton, emitting an electron and an antineutrino. This transformation changes the element itself, increasing its atomic number and thus creating a new, heavier element. Because the neutron flux in these events is so overwhelmingly high, this neutron capture happens much faster than the radioactive decay. This means that a nucleus can capture multiple neutrons in rapid succession before it has a chance to decay. This rapid capture allows for the creation of very heavy, neutron-rich isotopes. As these isotopes are formed, they are then ejected into the cosmos along with the rest of the supernova debris, or from the violent collision of neutron stars. These newly forged elements like gold, platinum, uranium, and all the other transuranic elements, are then dispersed throughout interstellar space. They become part of the cosmic dust and gas that will eventually coalesce to form new stars, new planetary systems, and perhaps even new worlds like our own. So the gold adorning a king's crown, the platinum in your electronics, the uranium powering a reactor, all of these incredibly heavy, precious, and powerful elements owe their very existence to the extreme, violent, and beautiful cosmic forges of neutron stars and supernova explosions. It is a testament to the universe's capacity for creation, even in its most destructive moments, that such fundamental building blocks of matter are born from the cataclysmic demise of stars. The dense embrace of a neutron star, a celestial pressure cooker of unparalleled intensity, is where the universe truly unlocks its potential to forge the heaviest and most exotic of elements, scattering them like cosmic seeds for future generations of celestial bodies. The heaviest elements, born in the fiery collapse and violent mergers of neutron stars, are the universe's most precious and potent gifts, scattered across the cosmos by celestial alchemy. The R-process symphony, rapid neutron capture and the creation of gold. Imagine, for a moment, the universe not as a static canvas, but as a dynamic, ever-evolving symphony. Within this grand cosmic orchestra, certain moments are marked by crescendos of unimaginable power, moments that give rise to the very elements that compose us and our world. One such powerful movement in this celestial symphony is known as the R-process, a name derived from rapid neutron capture. This is not a gentle, slow unfolding. This is a high-octane, high-intensity process that occurs under the most extreme conditions the universe can muster, conditions far beyond anything we can replicate safely on Earth. The R-process is the primary cosmic engine responsible for forging many of the heaviest elements in the periodic table, those elements that are too massive and unstable to be created through the slower, more sedate processes found within the steady burn of stars. Think of elements like gold, platinum, uranium, and the very rare earth elements essential for our modern technologies. Without the R-process, these precious and powerful materials would simply not exist. So, where does this explosive symphony play out? The leading candidates for the sites of the R-process are the cataclysmic explosions of neutron stars, specifically, the incredibly violent merger of two neutron stars. Neutron stars themselves are the incredibly dense remnants of massive stars that have reached the end of their lives and collapsed under their own gravity. Imagine squeezing the mass of our Sun into a sphere only about 20 kilometers in diameter. That's the density we're talking about. A teaspoon of neutron star material would weigh billions of tons. When two such incredibly dense objects collide, the forces involved are staggering. The merger unleashes a torrent of neutrons, a veritable storm of these fundamental particles. In these fleeting, violent moments, atomic nuclei are bombarded with an overwhelming number of neutrons. Nuclei, which are composed of protons and neutrons, are typically stable within certain limits. However, when faced with such an intense barrage of neutrons, they can absorb them at an astonishing rate, far faster than they can undergo radioactive decay. This rapid absorption is the hallmark of the R-process. A nucleus might absorb a dozen or more neutrons in mere seconds. This creates extremely neutron-rich isotopes, which are highly unstable. As these newly formed, neutron-rich nuclei are created, they are still within the incredibly energetic environment of the neutron star merger. However, as the explosion expands and cools, these unstable isotopes begin their rapid transformation. They undergo a series of beta decays. In a beta decay, a neutron within the nucleus transforms into a proton, emitting an electron and an antineutrino. This process increases the atomic number of the element, effectively changing it into a different element. For example, a highly neutron-rich isotope of iron might absorb neutrons, then undergo beta decay, transforming into a heavier element, and then absorb more neutrons, and so on. This chain reaction of neutron capture and beta decay continues, pushing the newly formed elements up the periodic table towards the heaviest and most precious ones. Consider gold. A single atom of gold has 79 protons. To create gold through the R-process, a lighter nucleus must absorb a significant number of neutrons and then undergo a series of beta decays until it reaches an atomic number of 79. This entire process happens in an environment of extreme energy, density, and neutron flux. The conditions are so extreme that the very fabric of spacetime is warped. The temperatures can reach billions of degrees Celsius, and the densities are so high that matter behaves in ways that are difficult for us to fully comprehend. The gravitational waves detected from the merger of two neutron stars in 2017 provided crucial observational evidence supporting the R process as the source of these heavy elements. The specific light signatures, or spectra, observed after the merger showed the presence of elements like gold and platinum, directly linking these events to their creation. This was a monumental aha moment for astrophysicists, confirming that these cosmic collisions are indeed the stellar forges where our most prized elements are born. The R process is more than just a chemical reaction. It is a fundamental cosmic event that shapes the elemental composition of the universe. It's a testament to the universe's capacity for creation, even in its most violent and chaotic moments. It reminds us that the very atoms that make up our bodies, the gold in our jewelry, and the rare earth elements in our devices, all have a grand and dramatic origin, forged in the heart of stellar explosions and the fiery dance of colliding neutron stars. And so, the universe orchestrates its most precious creations through a symphony of rapid neutron capture, a cosmic ballet of destruction and rebirth, where the heaviest elements, like gold, find their genesis in the inferno of colliding stars, a reminder that even in the most extreme violence, profound beauty and essential elements are born. The S process serenade, slow neutron capture in dying stars. Deep within the quiet, fading embers of certain stars, a more gentle, yet equally profound atomic creation takes place. Unlike the explosive fury of a supernova, this process, known as the S process, unfolds with a deliberate, almost tender pace. It is a serenade of neutron capture, a patient building of heavier elements from lighter ones within the stable, evolving cores of stars that are reaching the end of their lives. Imagine a star, perhaps a red giant, swollen and cooler on its surface, but with an intensely active interior. Here, in these venerable stellar bodies, free neutrons are not as abundant as in a supernova, but they are present, and they are captured by atomic nuclei one by one, slowly, steadily. This isn't a frantic bombardment, it's a deliberate, measured interaction. When a nucleus absorbs a neutron, it becomes a heavier isotope of the same element. If this new isotope is unstable, it will eventually undergo beta decay, transforming a neutron within its nucleus into a proton. This transformation is crucial as it changes the element itself, moving it up the periodic table. For example, a nucleus might capture a neutron, becoming a heavier isotope. If that isotope then undergoes beta decay, it becomes a new element, one atomic number higher. This process is slow because the rate of neutron capture is significantly slower than the rate of radioactive decay for many of the intermediate isotopes. This allows the nucleus time to beta decay before it has a chance to capture another neutron. It's this relative timing, the slow capture and the possibility of decay in between, that defines the S process. It's responsible for the creation of many elements in the middle of the periodic table, elements like strontium, barium, and even some of the heavier ones like lead. These elements, forged not in cataclysm but in the slow, internal processes of aging stars, are then eventually released into the cosmos when these stars shed their outer layers, becoming planetary nebulae, or when they eventually transform into white dwarfs. The S process is a testament to the fact that creation in the universe isn't always about violence and spectacle. Sometimes, it is a quiet, extended song, sung by dying stars, that enriches the cosmic tapestry with the very elements that will one day form new worlds and new life. It's a reminder that even in decline, there is profound creation, a gentle unfolding of complexity from simplicity, a celestial lullaby that echoes through the vastness of space, contributing its unique harmonies to the grand symphony of atomic existence. The S process is a delicate art, a slow unfolding of atomic destiny within the quiet heart of a star, painting the universe with pigments of strontium and barium. Cosmic dust grains, the microscopic seeds of new atomic compositions. Beyond the grand, explosive events, the universe also orchestrates creation on a scale almost too small to perceive. The humble cosmic dust grain. These are not mere specks of dirt, but rather the microscopic, silent artisans of atomic composition, carrying within them the remnants of stellar lives and the potential for entirely new worlds. Imagine, if you will, vast clouds of gas and plasma illuminated by the distant glow of newborn stars. Within these nebulae, the very elements forged in the hearts of dying suns begin to coalesce. These are the building blocks, the fundamental atoms of hydrogen, helium, and the heavier elements like carbon, oxygen, and iron that have been scattered across the cosmos by stellar winds and supernova explosions. As these atoms drift through the interstellar medium, they encounter conditions that allow them to begin to gather. It's a slow, patient process, driven by the subtle forces of gravity and electrostatic attraction. Initially, a single atom might attract another, forming a simple molecule. Then, this nascent cluster might attract more atoms, or perhaps other small clusters. Over immense stretches of time, these gatherings grow, layer by layer, atom by atom. The surfaces of these tiny particles become active sites, where gas molecules can collide, react, and even freeze onto them, further increasing their size and complexity. Think of it like frost forming on a windowpane, but on an unimaginably grand scale and across cosmic distances. These dust grains are not uniform. They are incredibly diverse, reflecting the varied origins of their constituent atoms. Some may be rich in carbon, formed in the cooler outer layers of carbon-rich stars, while others might be silicates, composed of silicon and oxygen, originating from stars that eventually shed their outer envelopes in dramatic planetary nebulae. Still others could be metallic, composed of iron and nickel, the products of the most violent stellar deaths. These grains are incredibly small, often only a few hundred nanometers across, smaller than the wavelength of visible light. Yet their collective presence is immense, forming significant portions of interstellar clouds and playing a crucial role in the formation of new stars and planetary systems. They act as catalysts, providing surfaces upon which chemical reactions can occur that might not otherwise happen in the diffuse gas. They also absorb and re-emit starlight, influencing the temperature and chemistry of their surroundings, and providing the crucial shielding that allows molecules to form and persist in the harsh environment of space. These dust grains are the vital intermediaries, the tangible link between the diffuse elemental soup of the interstellar medium and the dense, complex structures of planets and even life itself. They are, in essence, the universe's quiet alchemists, meticulously gathering and arranging the fundamental particles into the seeds of future cosmic wonders. The very composition of these grains, dictated by the types of stars that created their atoms and the environments in which they formed, carries a unique story, a whisper of their stellar parentage and their potential destiny. They are the scattered remnants of past stellar cycles, patiently waiting to be incorporated into the next grand act of cosmic creation. Their journey from stellar remnants to planetary building blocks is a testament to the universe's persistent drive towards complexity, a subtle yet profound process that underpins the very existence of everything we know. Within the dust, the echoes of creation patiently gather, whispering possibilities for all that is yet to be. Stellar winds carry creation, dispersing newly forged elements into space. Imagine, for a moment, the most magnificent of engines, vast beyond our earthly comprehension, burning with an intensity that can only be described as celestial. These are the stars, the cosmic furnaces we've been exploring, and their role in the grand tapestry of atomic creation extends far beyond the brilliant fusion within their cores. While they are the birthplace of elements, they are also their tireless disseminators. As stars evolve, particularly as they reach the later stages of their lives, they begin to expel the very material they have so painstakingly crafted. This expulsion isn't a gentle sigh. It is often a powerful, continuous outflow of particles and energy known as stellar winds. These winds are not merely fleeting gusts of gas. They are potent streams of plasma, charged particles, and crucially, the newly synthesized atoms that have emerged from the star's fiery heart. For stars like our Sun, these winds are a constant, albeit relatively gentle, breeze. They carry away a small fraction of the star's mass over billions of years, but even this steady outflow contributes to the interstellar medium, the diffuse gas and dust that permeates the space between stars. However, it is in the more dramatic life cycles of stars, particularly the more massive ones, that stellar winds play their most significant role in cosmic dispersal. When a massive star exhausts its nuclear fuel, it doesn't simply fade away. Instead, it can undergo a series of energetic events, including pulsations and powerful stellar winds that can shed a substantial portion of its outer layers. These ejected layers are rich with the heavy elements forged during the star's active life. Elements like carbon, oxygen, neon, magnesium, silicon, and even iron, all meticulously assembled through the process of nucleosynthesis. Consider the red giant phase of a star like our Sun, or the even more dramatic Wolf-Rayet phase of massive stars. In these stages, the star's outer atmosphere expands enormously, becoming cooler and more diffuse. Stellar winds from these expanded envelopes can be incredibly strong, carrying away material at speeds of hundreds or even thousands of kilometers per second. For a red giant, this mass loss can be significant enough to form a planetary nebula, a beautiful, glowing shell of gas and dust that surrounds the dying star. This nebula is not just a spectacle of light. It is a cosmic scattering of the elements that the star has accumulated over its lifetime, seeding the surrounding interstellar space with the building blocks for future generations of stars and planets. Massive stars in their final throes often experience even more violent expulsions. Before their ultimate supernova explosion, they can unleash powerful stellar winds that strip away their outer envelopes, exposing the core and enriching the interstellar medium with a cocktail of heavy elements. These winds are like cosmic exhalations, carrying away the star's stellar biography, atom by atom, into the vastness. This process is fundamental to the chemical evolution of the universe. Without these stellar winds, the elements heavier than hydrogen and helium would remain locked away within the stars, and the cosmos would be a far simpler, less diverse place. The very existence of planets like Earth, with their complex chemistries and diverse geological compositions, is a testament to the efficacy of these stellar dispersal mechanisms. The elements forged in the core of a star do not simply remain there. Stellar winds act as a crucial distribution network, a cosmic delivery service that transports these precious, newly minted atoms out into the interstellar void. This ejected material mixes with existing interstellar gas and dust, gradually enriching it with heavier elements. Over vast cosmic timescales, this enrichment leads to a higher abundance of these elements in the molecular clouds from which new stars and planetary systems will eventually form. In essence, each star that lives and dies, through its stellar winds and explosive finales, contributes to the cosmic inheritance, providing the raw ingredients for the next cycle of cosmic creation. The atoms that make up our bodies, the very elements that form the earth beneath our feet, have, in large part, been carried to us on the winds of dying stars, a profound and beautiful testament to the interconnectedness of all matter in the universe. The winds from stars, like cosmic sighs, disperse the universe's alchemical treasures across the vast cosmic canvas. Planetary disks gather stardust, the raw materials for new worlds. Imagine, if you will, the quiet aftermath of a star's grand finale, or perhaps the gentle exhalation of a star in its mature years. These celestial events, though distant and often unseen, are the architects of the universe's fundamental building blocks. When stars forge heavier elements within their fiery cores, they don't hoard this cosmic wealth. Instead, through stellar winds and the cataclysmic explosions of supernovae, these newly created atoms are dispersed into the vast interstellar medium. This medium, often appearing as ethereal nebulae, is not empty space. It is a rich soup of gas and dust, a cosmic pantry brimming with the results of billions of years of stellar alchemy. Within these nebulae, gravity, that patient, persistent force, begins its subtle work. It draws together these scattered atoms, the carbon, oxygen, iron, silicon, and all the other elements that have been meticulously crafted by stellar furnaces. As these particles coalesce, they form denser clouds, regions where the gravitational pull becomes significant enough to overcome the outward pressure of the gas. These are the stellar nurseries, the very cradles from which new stars and their accompanying planetary systems will eventually emerge. When a new star igniescent within such a cloud, it doesn't consume all the surrounding material. A significant portion of this gas and dust, still orbiting the nascent star, flattens into a vast, spinning disk. This is the protoplanetary disk, a swirling, luminous disk of stardust, a cosmic potter's wheel poised to shape worlds. Within this disk, the finely dispersed atoms and molecules, the very stardust that has journeyed across unimaginable distances and undergone profound transformations, begin to play their crucial role. They are no longer just scattered remnants. They are the raw ingredients, the fundamental Lego bricks of the cosmos, ready to be assembled into something far grander. The tiny dust grains, each a minuscule repository of stellar history, begin to stick together. Electrostatic forces, similar to how a balloon rubbed against hair can attract small pieces of paper, cause these grains to clump. Over time, through countless gentle collisions, these small clumps grow into pebble-sized aggregates, then into larger rocks, and eventually into planetesimals, the building blocks of planets. The composition of this disk is a direct reflection of the elements forged in the stars that preceded the sun. Near the young star, where temperatures are higher, only refractory materials, those that can withstand heat, like metals and silicates, can condense. Further out in the colder reaches of the disk, volatile compounds like water ice, ammonia, and methane can also form and contribute to the growing bodies. This intricate process, driven by gravity and the inherent properties of the elements, is how the raw materials, the stardust of the universe, are meticulously gathered and organized, setting the stage for the emergence of new worlds. The stardust, once scattered and formless, now finds itself on a grand trajectory, destined to become the very fabric of planets. And so, the scattered dust of ancient stars, gathered by gravity's gentle hand, becomes the very foundation upon which new worlds are born. Accretion's patient work, building planets atom by atom. Imagine, if you will, a vast, swirling cloud of gas and dust, the remnants of a long-dead star, or perhaps the primordial soup of the early universe. This is the birthplace of stars and planets, a cosmic nursery where the fundamental building blocks of existence are gathered. Within this nebula, gravity, that gentle, persistent force, begins its meticulous work. It pulls together the scattered atoms, the hydrogen, the helium, the trace amounts of heavier elements forged in stellar furnaces, and the dust grains, those microscopic specks of solidified stardust. This process, this gradual gathering and clumping, is known as accretion. It's not a sudden, dramatic event, but a slow, patient accumulation, a cosmic ballet of attraction and coalescence. At first, these clumps are tiny, mere millimeters across, akin to dust bunnies in a quiet room. But as they drift through the nebula, they encounter more particles, more dust, and they grow. Each collision, each gentle embrace, adds to their mass, their gravitational pull. These larger clumps, now perhaps the size of pebbles or small rocks, are called planetesimals. They are the embryonic planets, the seeds from which worlds will eventually grow. These planetesimals continue their journey, orbiting the nascent star at the center of the disk. Their paths inevitably intersect, and when they do, gravity takes over. Smaller planetesimals are drawn into the gravitational embrace of larger ones, their matter adding to the growing planetary body. This is a violent, yet ultimately constructive process. Collisions can be catastrophic, shattering some bodies, but they also serve to merge others, accelerating the growth of the larger ones. The composition of these growing planets depends heavily on their distance from the central star. Closer to the star, where temperatures are higher, only rocky and metallic materials can condense and accrete. These are the terrestrial planets like our own Earth, Mars, Venus, and Mercury. Further out in the colder regions of the protoplanetary disk, volatile compounds like water ice, methane, and ammonia can also solidify. This allows for the formation of much larger bodies, the gas giants and ice giants like Jupiter, Saturn, Uranus, and Neptune. These giants, through their immense gravitational pull, then become dominant forces in their regions, sweeping up much of the remaining gas and dust, and even capturing smaller planetesimals. The process of accretion continues for millions, even tens of millions of years. It's a period of intense bombardment, where the surfaces of the young planets are constantly being reshaped by impacts. But through it all, the underlying process of gravitational attraction and accumulation remains the driving force, patiently building worlds from the scattered atoms of the cosmos. Each atom, each molecule, each dust grain, playing its small but essential role in the grand construction of a planet. It's a testament to the power of small beginnings and persistent forces, a reminder that even the most magnificent structures in the universe began as mere whispers of matter, drawn together by the subtle, yet undeniable pull of gravity. And so, from the scattered dust of the cosmos, through the patient, persistent embrace of gravity, worlds are sculpted, atom by atom, a testament to the universe's quiet, ongoing act of creation. The carbon cornerstone, life's essential building block forged in stars. And so, as our quiet exploration drifts through the cosmic tapestry, we arrive at a truly remarkable chapter, a story woven not just from light and gravity, but from the very essence of existence. We turn our gaze now to carbon, a cornerstone element, the fundamental architect of all known life, and a testament to the profound, intricate processes that unfolded in the fiery hearts of stars. Imagine, for a moment, the universe as a vast, silent workshop and stars as its tireless artisans. For billions of years, these celestial furnaces have been engaged in a grand alchemical endeavor, transforming the simplest of elements into the complex, diverse building blocks that would eventually give rise to planets, to oceans, and to ourselves. The journey of carbon is a prime example of this stellar artistry. It begins, as so many things do, with the most abundant element in the cosmos, hydrogen. Within the immense pressures and temperatures of a star's core, hydrogen atoms fuse, creating helium. This is the primary energy source for stars, the gentle hum of creation that sustains them for eons. But the story doesn't end there. In stars that are sufficiently massive, a further stage of fusion can occur. Helium nuclei, themselves born from the union of hydrogen, can collide and fuse. This is where carbon enters the cosmic stage. Under the intense gravitational squeeze and searing heat, 3 helium nuclei can merge. This process, known as the triple alpha process, is a delicate dance of quantum mechanics and nuclear physics. It's not a simple, straightforward reaction. It requires specific energy states, a kind of cosmic resonance, for it to occur efficiently. If these conditions are not met, the helium might simply remain helium, or perhaps fuse into unstable isotopes that quickly decay. But in the right stellar environments, these 3 helium nuclei lock together, forming a stable carbon nucleus. This is a pivotal moment, a grand act of creation that laid the groundwork for the intricate chemistry of life. Carbon, with its unique atomic structure, has a remarkable ability to form stable bonds with itself and with other elements. It can create long chains, rings, and complex three-dimensional structures, forming the backbone of organic molecules. Think of proteins, DNA, carbohydrates. All of these are built upon a framework of carbon atoms. Without this stellar forging of carbon, the very possibility of life as we understand it would be absent from the universe. The carbon created in these stellar cores doesn't remain trapped forever. As stars evolve, particularly those that reach the end of their lives in spectacular supernova explosions, they disperse these newly forged elements, including carbon, into the interstellar medium. This enriched material then becomes the raw ingredient for new generations of stars and planets. So when we look at a leaf, at the intricate patterns of a snowflake, or indeed, at the very cells that make up our bodies, we are witnessing a direct legacy of stellar processes, of the fusion furnaces that burned billions of years ago. The carbon that defines our existence was once part of a star, a fundamental element brought into being by the immense power and precision of cosmic alchemy. It's a profound connection, a reminder that we are, quite literally, stardust, and that the building blocks of our being were forged in the very fires that light up our night sky. The creation of carbon in stars is not merely a scientific fact. It is a poetic narrative of cosmic evolution, a story of how the universe, through its fundamental laws, has generated the conditions necessary for complexity and life to emerge. It speaks to a universe that is not static, but dynamic, constantly creating, transforming, and seeding the cosmos with the potential for wonder. The carbon forged in starlight is the silent architect of our very breath, a cosmic inheritance connecting our fleeting lives to the enduring furnaces of the universe. Oxygen's breath of life, a byproduct of stellar fusion. Deep within the fiery hearts of stars, a process of profound transformation unfolds, a process that has, over eons, gifted our universe with the very essence of breath. We speak, of course, of oxygen, an element so fundamental to our existence that its presence often goes unnoticed, a silent partner in every inhalation, every exhalation. Yet oxygen's story is not one of simple beginnings, but of cosmic artistry, a tale woven from the intense heat and pressure of stellar interiors. Its creation is not a primary goal of stellar fusion, but rather a beautiful, life-sustaining byproduct. To understand oxygen's origin is to peer into the very engines of creation, to witness how the universe, in its grand, unfathomable design, crafts the elements that allow life to flourish. We often think of stars as simply burning, as sources of light and heat, but they are also, in a very real sense, alchemical laboratories, diligently working to assemble the building blocks of everything we know. The dominant process for oxygen creation occurs in stars that are somewhat more massive than our own sun, stars that have long since exhausted their primary hydrogen fuel and have begun to fuse helium. This helium fusion, a process that occurs at incredibly high temperatures, typically around 100 million Kelvin, is where oxygen truly begins to emerge. In the core of these stars, helium nuclei, which consist of 2 protons and 2 neutrons each, undergo a series of reactions. The initial step involves the fusion of 3 helium nuclei to form a carbon nucleus. This is known as the triple alpha process, a crucial step in stellar nucleosynthesis. Once carbon is formed, it can then fuse with another helium nucleus. This reaction, a carbon-12 nucleus combining with a helium-4 nucleus, results in the creation of an oxygen-16 nucleus. This oxygen-16 is the most abundant isotope of oxygen and is the primary form produced through this stellar pathway. This process is not instantaneous. It is a slow, painstaking buildup, occurring over millions, even billions of years. The conditions within a star's core are so extreme that these nuclei, normally repelling each other due to their positive charges, are forced together with immense energy, overcoming their natural repulsion and fusing to form new, heavier elements. Imagine countless helium atoms stripped of their electrons in the searing heat, their nuclei colliding with unimaginable force. Each successful collision, each fusion event, adds to the growing abundance of carbon and then oxygen. But the story doesn't end there. In more massive stars, the fusion process can continue, leading to the creation of even heavier elements. However, the fusion of carbon and helium to produce oxygen is a particularly significant pathway because oxygen is a relatively stable nucleus. It is not so easily broken down or further fused in the immediate stages of stellar evolution. This stability allows oxygen to accumulate in the stellar core. As the star evolves and its internal structure changes, these elements are gradually mixed and transported. In some stars, particularly during their later stages, such as in the red giant phase, convection currents can bring the newly synthesized oxygen from the core to the outer layers. This is a critical juncture, as it allows these elements to be eventually expelled into interstellar space. For stars that end their lives in a spectacular supernova explosion, the oxygen they have painstakingly created is violently ejected, scattering this vital element across vast cosmic distances. This explosive dispersal is essential. Without supernovae, the oxygen created within stars would remain largely confined to those stellar remnants, inaccessible to the formation of new stars and planetary systems. The shockwaves from a supernova compress interstellar gas and dust, triggering the collapse of nebulae and initiating the birth of new generations of stars. And within these new nebulae, the oxygen forged in the hearts of long-dead stars becomes a fundamental component, a silent promise of future life. The oxygen that fills our lungs today, the oxygen that sustains our planet, is a direct descendant of these ancient stellar furnaces. It is a testament to the universe's capacity for intricate, life-enabling processes, a reminder that even the most commonplace elements have a majestic and dramatic origin. The very air we breathe is, in essence, stardust, a cosmic gift born from the intense alchemy of stellar fusion, a testament to the interconnectedness of all things in the vast expanse of the cosmos. The oxygen we inhale is a whisper from a dying star, a promise of life carried on the cosmic winds, a fundamental element born from stellar fire that now fuels our very existence. Nitrogen's vital cycle, essential for all known life. The very air we breathe, that invisible, life-sustaining blanket surrounding our planet, is composed of approximately 78% nitrogen. This seemingly inert gas, elemental nitrogen, N2, is remarkably stable, its 2 atoms bound together by a triple covalent bond so strong that it requires immense energy to break. This stability, while making it a crucial component of our atmosphere, also presents a significant challenge for life. Nitrogen is fundamental to the existence of all known life, forming the backbone of amino acids, the building blocks of proteins, and the nitrogenous bases that make up DNA and RNA, the very blueprints of life. Without nitrogen, the intricate machinery of biological processes simply could not function. Yet, most organisms, including plants and animals, cannot directly utilize atmospheric nitrogen. They are, in essence, surrounded by a vast reservoir of essential material that is largely inaccessible to them. This is where the concept of the nitrogen cycle becomes profoundly important, a testament to the intricate interconnectedness of Earth's systems. The nitrogen cycle is a biogeochemical process that describes the transformation of nitrogen and nitrogen-containing compounds in nature. It's a continuous journey, a perpetual dance of atoms moving between the atmosphere, the soil, and living organisms. The cycle is driven by a complex interplay of biological, chemical, and geological processes, orchestrated by a diverse array of microorganisms, primarily bacteria, that possess the unique ability to break the formidable triple bond of atmospheric nitrogen. The first crucial step in making atmospheric nitrogen available to life is called nitrogen fixation. This process converts gaseous nitrogen into ammonia, NH3, or related nitrogenous compounds that can be assimilated by plants. Nitrogen fixation can occur through several pathways. The most significant biological pathway is carried out by specialized nitrogen-fixing bacteria. Some of these bacteria live freely in the soil, while others form symbiotic relationships with plants, most notably with legumes like peas, beans, and clover. In these symbiotic relationships, the bacteria reside in nodules on the plant's roots, receiving carbohydrates and a protective environment from the plant in return for a steady supply of fixed nitrogen. These tiny microbial powerhouses are the unsung heroes of our biosphere, tirelessly working to unlock the potential of atmospheric nitrogen. Another significant pathway for nitrogen fixation is atmospheric fixation, which occurs during lightning storms. The immense electrical energy of lightning can break the strong triple bond in nitrogen molecules, allowing them to combine with oxygen to form nitrogen oxides, NOx. These oxides then dissolve in rainwater, forming nitrates, NO, that are carried to the Earth's surface, providing a natural source of nitrogen for plants. Industrial processes, such as the Haber-Bosch process, also fix nitrogen artificially, producing ammonia for fertilizers, which has dramatically altered global agriculture but also has significant environmental implications. Once nitrogen is fixed into a usable form, plants can absorb it from the soil, primarily as ammonium NH4+, or nitrate NO, through their root systems. These inorganic nitrogen compounds are then incorporated into organic molecules within the plant, such as amino acids and nucleic acids. When animals consume plants, they obtain their nitrogen from these organic molecules. This is how nitrogen moves up the food chain, becoming an integral part of every living creature. However, the journey doesn't end there. When plants and animals die, or when animals excrete waste products, their organic nitrogen compounds are broken down by decomposers, such as bacteria and fungi, in a process called aminification. These decomposers release the nitrogen back into the soil in the form of ammonia. From here, the nitrogen can take another vital turn in the cycle. In aerobic oxygen-rich conditions, certain bacteria known as nitrifying bacteria convert ammonia into nitrites NO, and then into nitrates NO through a process called nitrification. Nitrates are the most readily absorbed form of nitrogen by most plants, completing the loop from soil to plant. However, in anaerobic oxygen-poor conditions, Other bacteria called denitrifying bacteria carry out denitrification. This process converts nitrates back into gaseous nitrogen, N2, which is then released back into the atmosphere, completing the cycle. This denitrification is crucial for preventing the excessive accumulation of nitrogen compounds in the soil and water, and for maintaining the balance of atmospheric nitrogen. The nitrogen cycle is a dynamic and complex system, sensitive to environmental changes. Human activities, particularly the widespread use of synthetic fertilizers, have significantly impacted the natural nitrogen cycle. The excessive application of fertilizers leads to increased nitrogen runoff into rivers and oceans, causing eutrophication, harmful algal blooms, and oxygen depletion in aquatic ecosystems. Furthermore, the production of fertilizers is an energy-intensive process that contributes to greenhouse gas emissions. Understanding the nitrogen cycle is not just an academic pursuit. It is fundamental to comprehending the health of our planet and the sustainability of life itself. It highlights the indispensable role of microorganisms in maintaining the delicate balance of our biosphere and the profound interconnectedness of all living things through the circulation of this essential element. It's a constant, quiet exchange, a testament to the universe's ingenious design for perpetuating life, atom by atom. Nitrogen, the unseen architect of life, breathes in the air, sleeps in the soil, and awakens in every living cell, a ceaseless testament to the planet's enduring, vital rhythm. The iron in our blood, a legacy of ancient supernovae. Deep within each of us, in the very essence of our being, lies a profound connection to the cosmos. The iron that carries oxygen through our bloodstream, the very element that gives our blood its life-sustaining color, is not a product of Earth's gentle geological processes alone. Instead, it is a testament to the violent, spectacular deaths of stars that occurred billions of years ago, long before our solar system even began to coalesce. This is a story of cosmic alchemy, a narrative etched in the very atoms that compose us. To understand the iron in our blood is to understand a fundamental truth. We are, quite literally, made of stardust. The creation of iron, atomic number 26, is a pivotal moment in stellar evolution, marking a boundary in the fusion process that powers stars. Stars, in their main sequence phase, are giant nuclear furnaces, converting lighter elements into heavier ones through a process called nuclear fusion. This process begins with hydrogen fusing into helium, then helium into carbon, and so on, releasing immense amounts of energy that keep the star shining. For most of a star's life, this fusion chain proceeds smoothly, creating elements up to oxygen and neon. However, as the star exhausts its lighter fuel and its core contracts and heats up, it can begin to fuse heavier elements. The fusion of elements beyond iron requires more energy than it releases. This is because the binding energy per nucleon, a measure of the stability of an atomic nucleus, peaks at iron. Think of it like pushing a boulder uphill. It requires a significant input of energy to move it to a higher energy state. Once a star's core is predominantly iron, fusion can no longer provide the outward pressure needed to counteract the inward pull of gravity. This is the critical point, the precipice of a star's demise. When a massive star reaches this iron core stage, it can no longer sustain itself. Gravity begins to win, and the core collapses with astonishing speed. This catastrophic collapse triggers a rebound, a shockwave that propagates outwards through the star's outer layers, resulting in a supernova explosion, one of the most energetic events in the universe. It is within the incandescent heart of this supernova, amidst unimaginable temperatures and pressures, that the creation of iron and elements heavier than iron truly takes place. During the supernova, a torrent of neutrons is unleashed. These neutrons can be captured by atomic nuclei. If this capture happens rapidly, before the nucleus can undergo radioactive decay, it's called the R process, rapid neutron capture. This R process is the primary mechanism for creating the heaviest elements, including many of the isotopes of iron and elements beyond it, like gold, silver, and uranium. The sheer density of neutrons and the extreme energy of the explosion allow nuclei to rapidly absorb multiple neutrons, building up to form these heavier elements. These newly forged elements, including the iron that would one day find its way into our bodies, are then ejected into the interstellar medium. They are scattered across vast cosmic distances, mingling with existing gas and dust clouds. Over eons, these enriched clouds become the nurseries for new generations of stars and planetary systems. Our own solar system formed from such a cloud, a swirling nebula composed of hydrogen, helium, and the remnants of countless ancient stars, including the iron created in their explosive deaths. As our planet Earth formed, iron was a significant component of the accreting dust and gas. Its high density caused much of it to sink to the Earth's core during the planet's molten early stages, but a substantial amount remained in the mantle and crust. And through the complex biological processes that arose on Earth, iron became an indispensable element for life. In our red blood cells, iron atoms are the central component of hemoglobin, the protein responsible for binding to oxygen in the lungs and transporting it to every cell in our body. Without this iron, our cells would starve for oxygen, and life as we know it would be impossible. So, when you feel the steady rhythm of your heartbeat or take a deep, life-giving breath, remember that you are experiencing a profound cosmic legacy. The iron in your blood is a direct link to the fiery demise of stars that blazed and died billions of years ago. It is a reminder of the universe's grand, ongoing cycle of creation and destruction, a cycle that ultimately brought forth the very elements that make us, us. The iron in your veins, a whisper from a stellar past, beats with the rhythm of a universe reborn. Gold's cosmic journey, from stellar explosions to earthly treasures. Imagine, for a moment, a substance so precious, so captivating, that it has driven exploration, fueled empires, and adorned royalty for millennia. We speak, of course, of gold. But have you ever paused to consider its origins? Not the mines of Earth, but the vast, silent crucible of the cosmos. Gold, this radiant metal, is not merely a terrestrial treasure. It is a celestial artifact, a testament to the universe's most violent and profound events. Its story begins not with pickaxes and pans, but with the cataclysmic deaths of stars. The creation of elements heavier than iron, like gold, requires immense energy and a flood of neutrons, far beyond what occurs within the stable life of most stars. For a long time, scientists pondered how these precious, heavy elements came to be. They knew that stars fuse lighter elements into heavier ones, but this process has a limit. Inside the core of a star, the energy required to fuse elements beyond iron actually exceeds the energy released, effectively halting the process. So where did gold, with its atomic number of 79, come from? The answer lies in some of the most energetic phenomena in the universe. The explosive end of massive stars, known as supernovae, and the even more extreme, yet equally awe-inspiring, collisions of neutron stars. When a massive star exhausts its nuclear fuel, it can no longer support itself against the crushing force of its own gravity. It collapses inward, then violently rebounds in a supernova explosion. This explosion unleashes an incredible torrent of energy and, crucially, a vast number of neutrons. In the heart of this stellar inferno, a process called the R process, or rapid neutron capture, can occur. Here, atomic nuclei are bombarded with neutrons at an astonishing rate. If a nucleus captures a neutron, it becomes unstable and quickly undergoes beta decay, transforming a neutron into a proton and emitting an electron. This change in the number of protons alters the element itself. During an R-process event, a nucleus can capture many neutrons in rapid succession before it has time to decay. This builds up very heavy neutron-rich isotopes. As the supernova expands and cools, these unstable isotopes eventually decay through a series of steps, ultimately forming stable, heavy elements like gold, platinum, and uranium. However, supernovae, while powerful, might not be the primary source of all the gold in the universe. Recent observations and theoretical models strongly suggest that the merger of two neutron stars, the incredibly dense remnants of smaller stellar explosions, is a far more efficient factory for producing these heavy elements. Neutron stars are essentially giant atomic nuclei, packed together with immense density. When two of them spiral into each other and collide, the resulting explosion is one of the most energetic events in the cosmos. This merger unleashes an even greater abundance of neutrons and provides the extreme conditions necessary for the R process to operate at its peak. The sheer scale of neutron flux during such an event is unparalleled, allowing for the rapid creation of the heaviest elements, including gold, in significant quantities. Once forged in these cosmic cauldrons, these newly created gold atoms, along with all other elements, are dispersed into the interstellar medium. They become part of vast clouds of gas and dust, the nebulae that drift through the galaxies. Over billions of years, these nebulae condense under gravity, forming new stars and planetary systems. Our own solar system, including Earth, formed from such a cloud of interstellar material, enriched with the byproducts of countless stellar explosions and neutron star mergers that occurred long before our sun was born. So, when you behold the gleam of gold, whether in jewelry, ancient artifacts, or even the subtle traces within our planet's crust, you are looking at the distilled essence of cosmic violence, a tangible piece of stellar history. Each atom of gold on Earth carries within it the memory of unimaginable energies, a silent narrative of stars that lived, died, and scattered their precious creations across the vastness of space, ultimately finding their way to us. The gleam of gold whispers tales of stellar death and cosmic mergers, a radiant echo of the universe's most explosive moments, now resting in the quiet embrace of our world. The Silicon Foundation, the backbone of Earth's geology. Silicon, a humble element, stands as the fundamental cornerstone of our planet's very structure. It is the silent architect of mountains, the invisible binder of soils, and the pervasive presence in nearly every rock and mineral that graces Earth's crust. Its journey to becoming the backbone of our geology is a story woven through the grand tapestry of cosmic creation, a narrative of stellar furnaces and the patient accumulation of matter over billions of years. In the early universe, shortly after the Big Bang, the primary elements were hydrogen and helium. The creation of silicon, a heavier element, required the intense, high-pressure environments found within stars. Stars, particularly those more massive than our Sun, act as cosmic alchemists. Deep within their cores, immense gravitational forces and extraordinarily high temperatures initiate nuclear fusion. In this process, lighter atomic nuclei are compelled to merge, forming heavier ones. Initially, stars fuse hydrogen into helium. As they evolve and exhaust their hydrogen fuel, they begin fusing helium into carbon, and then carbon into even heavier elements. Silicon is primarily forged during the later stages of a star's life, through processes involving the fusion of carbon and helium, or oxygen and neon. These fusion reactions are incredibly energetic, releasing vast amounts of light and heat that power the stars themselves. However, the creation of silicon doesn't happen in just any star. It's a hallmark of stars that have reached a significant stage of their evolution, often those destined for a dramatic end. Once silicon is synthesized within the stellar core, it becomes part of the star's elemental composition. But how does this silicon, born in the heart of distant stars, find its way to form the very ground beneath our feet? The answer lies in the explosive deaths of these stars, particularly through supernovae. When massive stars exhaust their nuclear fuel and can no longer support themselves against their own immense gravity, they collapse catastrophically. This collapse triggers a tremendous explosion, a supernova that blasts the star's outer layers, enriched with newly synthesized elements like silicon, out into the vast expanse of interstellar space. This ejected material, the remnants of stellar death, then disperses, mingling with existing nebulae and interstellar gas clouds. Over eons, gravity begins to pull these dispersed elements together. In regions where new stars and planetary systems are forming, vast clouds of gas and dust, known as nebulae, collapse under their own weight. Within these swirling nurseries, the silicon, along with countless other elements forged in previous stellar generations, becomes incorporated into the forming protoplanetary disk. This disk is a flat, rotating structure of gas and dust that surrounds a young star. As the disk coalesces, dust grains collide and stick together, gradually growing larger. Silicon, being a relatively abundant element in these clouds, plays a crucial role in this process. It forms the basis of silicate minerals, which are compounds containing silicon and oxygen, often bonded with other elements like magnesium, iron, aluminum, and calcium. These silicate minerals are the fundamental building blocks of most terrestrial planets, including our own Earth. As the Earth formed through accretion, the process by which smaller bodies merge to form larger ones, silicon-rich dust grains and planetesimals clumped together. The intense heat and pressure during Earth's formation caused differentiation, a process where denser materials sank to the core and lighter materials rose to the surface. Silicon, combined with oxygen to form silicate minerals, is less dense than iron and nickel, so it predominantly resides in the planet's mantle and crust. The vast majority of Earth's crust, approximately 90%, is composed of silicate minerals. Minerals like quartz silicon dioxide, feldspar, mica, and olivine are all silicon-based and form the bedrock of our continents and ocean floors. These minerals, in turn, form the rocks that shape our landscapes: granite, basalt, sandstone, and shale, to name just a few. Silicon's unique chemical properties, particularly its ability to form strong covalent bonds with oxygen and other elements, make it exceptionally stable and durable. This stability is why silicate rocks have persisted for billions of years, forming the geological record that scientists study to understand our planet's history. The very mountains we admire, the soils that nourish our crops, and the sands that stretch across deserts are all testaments to silicon's enduring presence, a direct consequence of its fiery birth in the hearts of ancient stars and its patient journey through the cosmos to become the very foundation of our world. The silicon that forms our planet's sturdy bones, a cosmic legacy of stellar furnaces, reminds us that even the ground beneath our feet is a testament to the universe's grand, ongoing story of creation. Rare earth elements' hidden power, forged in extreme cosmic events. The elements we often overlook, the rare earths, possess a quiet yet profound power, woven into the very fabric of our modern world. Think of your smartphone, the powerful magnets in electric vehicles, the vibrant colors in advanced displays, even the precision of medical imaging, all rely on these often unseen components. Yet, their story begins not in laboratories or mines, but in the most cataclysmic and energetic events the cosmos can muster. Unlike the more common elements like carbon or oxygen, which are forged in the steady furnaces of stellar interiors, or even iron, which marks the limit of that fusion process, the creation of rare earth elements, along with many other heavy metals, demands a far more extreme environment. These elements, a group of 17 chemically similar metallic elements including lanthanum, cerium, neodymium, and dysprosium, are not rare in terms of their abundance in the Earth's crust, but rather in their concentration into economically viable deposits. Their true rarity lies in their fiery birth. The primary mechanism for their creation is thought to be the rapid neutron capture process, or the R process. This process occurs in environments where a colossal number of neutrons are available for a very short period, allowing atomic nuclei to absorb neutrons at a rate faster than they can undergo radioactive decay. Imagine a cosmic forge, supercharged beyond comprehension. The most favored sites for this explosive nucleosynthesis are believed to be the merger of two neutron stars, the incredibly dense remnants of massive stars that have already undergone supernova explosions. When these two stellar corpses collide, the resulting event is one of the most energetic in the universe, releasing an immense flood of neutrons. In this fleeting, hyperenergetic crucible, lighter atomic nuclei are bombarded with neutrons, rapidly increasing their atomic mass. As they absorb these neutrons, they become highly unstable and undergo beta decay, transforming neutrons into protons and emitting electrons. This process effectively builds up heavier and heavier elements. The rarity of these events, the precise conditions required, and the subsequent dispersal of these newly forged elements through powerful outflows mean that the building blocks for rare Earths are scattered across the galaxy, only occasionally coalescing into concentrations that we can later find on planets like our own. Another potential site for the R process is the explosion of a certain type of supernova, known as a collapsar, where the core of a massive star collapses to form a black hole, and a powerful jet is launched outward. These extreme cosmic collisions and explosions are the cosmic furnaces, where the very atoms of rare Earth elements are painstakingly assembled, atom by atom, in a ballet of neutrons and radioactive decay, a testament to the universe's capacity for creating complexity from chaos. Their journey from these violent cosmic origins to their indispensable roles in our everyday technologies is a profound narrative of cosmic recycling and the enduring legacy of stellar death. These elements, born in the cataclysmic embrace of dying stars, now hold the quiet power to shape our world. The uranium legacy, the ultimate heavy element born in supernovae. Deep within the heart of the cosmos, a profound narrative of creation unfolds, a story etched in the very fabric of existence. We often speak of the elements that build our world, the carbon in our bodies, the iron in our blood, the silicon beneath our feet. But what of the elements that lie at the very edge of possibility, the heaviest, most unstable, yet undeniably significant? Tonight, we turn our gaze towards uranium, a substance that embodies the extreme end of stellar alchemy, a testament to the universe's most violent and energetic processes. Uranium, with its atomic number of 92, stands as one of the heaviest naturally occurring elements, a grand finale to the stellar fusion process. Its creation is not a gentle, gradual affair. It is a cataclysmic event, a symphony of destruction and rebirth played out in the death throes of massive stars. While lighter elements like oxygen and carbon are forged in the steady, sustained nuclear furnaces of stars like our Sun, uranium requires a far more extreme environment. This is where the supernova, the explosive death of a star many times more massive than our own, enters the cosmic stage. Imagine a star at the end of its life, its core collapsing under its own immense gravity. This collapse triggers a shockwave that blasts the star's outer layers into the void, a spectacle of unimaginable power and brilliance. It is in this brief, incandescent moment, in the heart of this stellar explosion, that the conditions are ripe for the rapid synthesis of heavy elements. The process is known as the R process, for rapid neutron capture. In the incredibly dense and energetic environment of a supernova, atomic nuclei are bombarded by an overwhelming flux of neutrons. These neutrons are captured by existing atomic nuclei at an astonishing rate, far faster than the nuclei can decay. This rapid accumulation of neutrons effectively pushes the atomic nuclei beyond the stable limits of iron, the element that marks the end of fusion-powered element creation in stars. As more and more neutrons are added, the atomic nuclei become increasingly unstable, their protons and neutrons struggling to maintain cohesion. However, the sheer speed of the neutron bombardment outpaces the rate of radioactive decay. Nuclei are transmuted, growing heavier and heavier, step by step, through the addition of neutrons, until they eventually transform into the heaviest elements we know, including uranium. The energy released during these rapid neutron captures and subsequent beta decays is immense, contributing to the blinding light of the supernova itself. It is a process of creation born from utter destruction, a cosmic paradox. These newly forged uranium atoms, along with countless other heavy elements, are then flung outwards into interstellar space, becoming part of the vast cosmic dust clouds from which new stars and planets will eventually form. Our own solar system, and indeed our own planet Earth, is composed of these ancient stardust remnants, including the uranium that lies within our planet's crust. This uranium, a product of supernovae that occurred billions of years before our sun was even born, is a tangible link to the universe's violent past and its ongoing, grand alchemical processes. It is a reminder that even the most seemingly inert substances around us carry within them the echoes of cosmic explosions and the fundamental forces that shaped everything we know. The presence of uranium on Earth is not just a geological fact. It is a profound piece of cosmic history, a legacy of stellar death that continues to influence our world in subtle yet significant ways, from powering nuclear energy to contributing to the Earth's internal heat. And so, the heaviest elements, born from the explosive demise of ancient stars, find their way into the very foundations of our world, a silent testament to the universe's relentless cycle of creation and transformation. Cosmic rays' energetic touch, transmuting atoms in interstellar space. Imagine the vast emptiness between the stars, a seemingly serene void. Yet this interstellar medium is far from static. It is a dynamic arena, constantly bombarded by an invisible, relentless tide of energetic particles known as cosmic rays. These are not the gentle rays of sunlight. These are particles, primarily atomic nuclei, accelerated to nearly the speed of light by cataclysmic cosmic events like supernovae and active galactic nuclei. Their energy is immense, far exceeding anything we can produce in terrestrial particle accelerators. When these high-speed travelers encounter the sparse atoms of interstellar gas and dust, they don't simply pass by. They collide with tremendous force, like celestial billiards played at unimaginable speeds. These collisions are not merely physical impacts. They are profound interactions that can fundamentally alter the atomic structure of the target particles. A cosmic ray, perhaps a lone proton or a helium nucleus, can strike an atom of, say, carbon or oxygen, with such violence that it dislodges neutrons, protons, or even entire nucleons from the target nucleus. This process, known as spallation, is a powerful form of cosmic alchemy. It can transform one element into another, creating lighter isotopes or even entirely different elements altogether. For instance, the abundant helium in the universe is not solely a product of the Big Bang or stellar fusion. A significant portion is also generated through the spallation of heavier nuclei by cosmic rays. Similarly, the creation of lithium, beryllium, and boron, elements that are not efficiently produced in stars, is largely attributed to cosmic ray spallation. These elements are rarer, more delicate, and their very existence in the cosmic abundance we observe is a testament to the constant, energetic sculpting performed by cosmic rays. They are the universe's silent sculptors, chipping away at heavier atoms, and in doing so, creating the lighter, more foundational elements that will eventually contribute to the formation of new stars and planets. The interstellar medium, therefore, is not just a passive repository of matter. It is a grand cosmic laboratory where elements are continuously transmuted and rearranged by these energetic messengers from the far reaches of the cosmos. The very composition of the space around us is a dynamic tapestry, woven by the relentless bombardment of cosmic rays, a subtle but profound reminder that even in the deepest darkness, creation and transformation are ceaselessly at play. This constant, energetic interaction underscores the interconnectedness of all matter in the universe, where even the most distant and energetic phenomena can influence the very building blocks of existence, shaping the raw materials for future cosmic wonders. They are the universe's invisible hands, constantly reshaping the atomic landscape of the cosmos, a testament to the enduring power of energy and collision in the grand cosmic ballet. The energetic touch of cosmic rays, a silent, relentless force, reshapes the very atoms of interstellar space, reminding us that transformation is a fundamental constant of the universe, even in the quietest of voids, where stardust is perpetually reforged by celestial collisions. Radioactive decay, the universe's slow, constant atom transformation. The universe, in its vast and intricate tapestry, is not a static masterpiece but a dynamic, ever-evolving entity. Even within the seemingly immutable structure of atoms, a profound and constant transformation is underway. This process, known as radioactive decay, is a gentle yet relentless force, a slow and steady hand that reshapes the very building blocks of existence. It's a phenomenon that speaks to the impermanence of all things, yet also to the enduring cycles of creation and change that define our cosmos. Imagine the nucleus of an atom, a dense core of protons and neutrons, holding immense energy. For some atomic nuclei, this arrangement is inherently unstable. They possess an excess of energy or an unfavorable ratio of protons to neutrons. To achieve a more stable configuration, they must shed this excess energy or particles. This shedding is radioactive decay. It's not a violent, instantaneous event for most elements. Rather, it's a probabilistic one, a gradual release that can take millennia, millions, or even billions of years. This is where the concept of half-life comes into play, a fundamental aspect of radioactive decay. The half-life of a radioactive isotope is the time it takes for half of its atoms in a given sample to decay. This isn't a precise countdown for each individual atom, rather it's a statistical average. Some atoms might decay sooner, others much later, but over a large population of atoms, the half-life holds true with remarkable consistency. Think of it as a cosmic clock, ticking at its own unique pace for each radioactive element. For instance, uranium, a common isotope found in Earth's crust, has a half-life of about 4.5 billion years, roughly the age of our planet. This means that over billions of years, half of the original uranium-238 present when Earth formed has decayed into other elements, primarily lead. This decay process is not uniform. It can manifest in several ways. Alpha decay involves the emission of an alpha particle, which is essentially a helium nucleus, consisting of 2 protons and 2 neutrons. This reduces the atomic number and mass number of the parent atom, transforming it into a different element. Beta decay is another common form, where a neutron in the nucleus transforms into a proton, emitting an electron, a beta particle, and an antineutrino or vice versa. A proton transforms into a neutron, emitting a positron and a neutrino. This changes the atomic number but not the mass number, again resulting in a new element. Gamma decay, on the other hand, doesn't involve the emission of particles but rather high-energy photons, gamma rays. This usually occurs after alpha or beta decay, when the nucleus is still in an excited state and releases excess energy to reach a more stable configuration. These decay processes are not just abstract scientific curiosities. They have profound implications for our understanding of the universe and our place within it. Radioactive dating, for example, relies heavily on the predictable decay rates of certain isotopes to determine the age of rocks, fossils, and even archaeological artifacts, providing us with a window into Earth's deep past. The heat generated by radioactive decay within Earth's core is also a significant factor in geological processes, driving plate tectonics and volcanic activity. Furthermore, the study of radioactive elements has led to advancements in medicine, from diagnostic imaging to cancer treatment. The slow, constant transformation of atoms through radioactive decay is a testament to the universe's inherent dynamism. It's a reminder that even the most stable-seeming structures are subject to change, a continuous process of renewal and evolution that underpins the very fabric of reality. It is through these subtle, persistent shifts that the universe orchestrates its grander narratives, from the formation of elements to the shaping of worlds. The silent disintegration of unstable nuclei is not an end, but a profound continuation, a cosmic breath exhaling new forms and possibilities. Through atomic whispers, the universe gently rewrites its own story, atom by atom, in the quiet hum of eternal transformation. The Big Bang's fleeting moments, the creation of the lightest elements. Imagine, if you will, a moment of profound beginning, a cosmic dawn so ancient and so intense that our minds can barely grasp its scale. This is the story of the very first atoms, the primordial building blocks of everything we know, born in the fiery crucible of the Big Bang. For a brief, incandescent period in the universe's infancy, a mere few minutes after its inception, conditions were just right for the creation of the lightest elements, hydrogen and helium, and a tiny, almost imperceptible trace of lithium. Before this epoch, there were no atoms, no structures, just a searingly hot, incredibly dense soup of fundamental particles. As the universe rapidly expanded and cooled, protons and neutrons, themselves formed from even more fundamental quarks, began to interact. In the first few seconds, as temperatures dropped from an unimaginable trillion degrees Kelvin, protons and neutrons were abundant. Then, around the 1-second mark, as the universe cooled further to about 10 billion degrees Kelvin, these protons and neutrons began to fuse. This process, known as Big Bang nucleosynthesis, was not a slow, gradual buildup like in stars, but a rapid, furious burst of creation. Protons, the nuclei of hydrogen atoms, were the most prevalent. When 2 protons fused, they could form deuterium, an isotope of hydrogen with 1 proton and 1 neutron. Deuterium was a crucial intermediate step. Some deuterium nuclei then captured another proton to form helium-3, another hydrogen isotope. Alternatively, a proton could fuse with a neutron to form deuterium, and then this deuterium could fuse with another neutron to form a helium-4 nucleus, which consists of 2 protons and 2 neutrons. This helium-4 nucleus is incredibly stable, and it represented the end of the line for fusion in the Big Bang. The universe was expanding and cooling too quickly for more complex nuclei to form. It's a remarkable testament to the fundamental forces of nature that in this fleeting period, the universe established the relative abundance of hydrogen and helium that still dominates the cosmos today. Roughly 75% of the baryonic matter in the universe is hydrogen, and about 24% is helium, with only trace amounts of other elements. This precise ratio, dictated by the physics of those first few minutes, is a profound clue to the universe's origin. The creation of these light elements was a race against time and temperature. As the universe expanded, the density and temperature dropped, and the window for fusion closed. After about 20 minutes, the universe had cooled to a point where fusion was no longer possible. What remained was a plasma of these newly formed atomic nuclei and free electrons. It would take another 380,000 years for the universe to cool enough for electrons to combine with these nuclei, forming the first stable, neutral atoms and allowing light to travel freely for the first time, marking the era of recombination. But the foundational work, the very essence of atomic existence for the vast majority of matter, was laid in those first few minutes, a testament to the universe's initial, explosive artistry. In the briefest of cosmic breaths, the universe painted the first hues of existence, setting the stage for all that would ever be. The quantum realm's strange ballet, the ongoing creation of atomic structures. We often imagine the creation of atoms as a singular, grand event, a cosmic dawn where the very first hydrogen and helium atoms flickered into existence during the universe's fiery infancy. And indeed, that initial formation was a monumental and foundational moment. However, the story of atomic creation doesn't simply end there. It's a continuous, subtle, and profoundly intricate process that unfolds even now, in the hidden depths of what we call the quantum realm. This realm, the domain of the infinitesimally small, is where the fundamental rules governing matter are at play, and it's here that the very structures of atoms are not only maintained but, in a sense, perpetually recreated and defined. Think of it not as a static blueprint, but as a living, breathing dance. At the heart of every atom lies its nucleus, a dense collection of protons and neutrons bound together by the incredibly powerful, strong nuclear force. This force is one of the four fundamental forces of nature, and it operates on incredibly short distances, holding these positively charged protons, which would otherwise repel each other electrostatically, in a tight, stable embrace. The number of protons in the nucleus, known as the atomic number, is what fundamentally defines an element. A carbon atom always has 6 protons, an oxygen atom always has 8, and so on. This number is remarkably stable for most elements under typical conditions. However, the quantum realm introduces nuances. For elements with very large nuclei, particularly those beyond uranium, the strong nuclear force is in a constant tug-of-war with the electromagnetic repulsion between the protons. This delicate balance means these super-heavy elements are inherently unstable. They exist, but their existence is fleeting, governed by the probabilistic nature of quantum mechanics. They will eventually decay, transforming into lighter, more stable elements. This process of radioactive decay is a direct example of ongoing atomic transformation, a kind of self-creation and dissolution dictated by quantum rules. Beyond the nucleus, the electrons orbit in a way that defies classical intuition. They don't follow neat, predictable paths like planets around a sun. Instead, they exist in probability clouds or orbitals, regions of space where they are most likely to be found. The arrangement and energy levels of these electrons are governed by quantum numbers, which dictate their properties, their interactions, and ultimately the chemical behavior of the atom. The creation of these electron configurations is a constant quantum ballet. When an atom absorbs energy, an electron can jump to a higher energy orbital. When it releases energy, it falls back to a lower orbital, emitting a photon of light. This ceaseless exchange of energy, this quantum leap, is how atoms interact, how they form bonds, and how they participate in the vast array of chemical reactions that shape our universe. Furthermore, even in seemingly empty space, quantum fluctuations are occurring. Pairs of virtual particles and antiparticles can spontaneously pop into existence for incredibly brief moments before annihilating each other. While these are not directly creating stable atoms in the way stellar fusion does, they are a testament to the dynamic and energetic nature of the quantum vacuum, the fundamental substrate from which all reality, including atomic structures, emerges. The very act of observing a quantum system can influence its state, a concept known as the observer effect. This means that the creation and definition of atomic structures are not entirely independent of the universe's unfolding narrative. The universe is not just a collection of pre-made atoms. It is a continuous process of atomic becoming, governed by the elegant, albeit strange, rules of quantum mechanics. The stability of an atom, its identity, its potential to interact, all are manifestations of this ongoing quantum ballet. It is a dance of forces, probabilities, and energy exchanges that ensures the universe, at its most fundamental level, is in a perpetual state of subtle, yet profound creation. In the quantum realm, the structure of every atom is a fleeting, probabilistic masterpiece, perpetually composed and recomposed in the universe's quietest, most fundamental dance. The electrons dance, shaping the properties of every atom. The electron, a fundamental particle, plays a role far more profound than simply orbiting the nucleus. Its ethereal presence, its peculiar quantum nature, is the very architect of an atom's identity, dictating its behavior, its interactions, and ultimately, the properties of every substance in the cosmos. Imagine, if you will, a vast, invisible ballet happening constantly within the seemingly solid structure of matter. This dance isn't a chaotic frenzy, but a precisely orchestrated performance governed by the laws of quantum mechanics. Electrons don't orbit in neat, predictable paths like planets around a sun. Instead, they exist in probability clouds, regions of space where they are most likely to be found. These are called atomic orbitals, and their shapes and energies are unique for each type of atom. The number of electrons an atom possesses, and how they are arranged within these orbitals determines its chemical personality. For instance, atoms with a full outer electron shell are exceptionally stable and unreactive, like the noble gases. They have no desire to share or steal electrons, content in their balanced configuration. Conversely, atoms with nearly full or nearly empty outer shells are highly reactive, eager to engage in chemical bonds to achieve that coveted stable state. This dance of electrons, this constant striving for equilibrium, is the force behind all chemical reactions. When atoms interact, it is their outermost electrons that meet first, exchanging or sharing in a cosmic negotiation that forms molecules. The strength of these bonds, the angles at which atoms connect, the very color of a substance, all these macroscopic properties are directly traceable to the subtle, intricate dance of electrons. Consider the vibrant hues of a sunset. They are a testament to the specific energy transitions of electrons within atmospheric gases, absorbing and re-emitting light at particular wavelengths. Or the conductivity of a metal. This arises from loosely bound electrons that can easily move from one atom to another, forming an electrical current. Even the solidity of a table beneath your hand is an illusion created by the repulsive forces between the electron clouds of the atoms in your body and the atoms in the table. Without this intricate electron dance, The universe as we know it, with its diverse elements, compounds, and complex structures, would simply not exist. It is this unseen quantum ballet that imbues each atom with its unique character, a character that ripples outwards to define the very fabric of reality. The electron's dance is not merely a physical phenomenon. It is the fundamental language of chemistry, the silent composer of all material existence, a testament to the profound elegance hidden within the smallest scales of the universe. The energy levels, the shapes of the orbitals, the very spin of these tiny particles, all contribute to a unique atomic fingerprint. This fingerprint dictates how an atom will behave when it encounters another. It determines whether it will readily give up an electron, accept one, or share them in a covalent bond. The arrangement of electrons in shells and subshells follows specific rules, like the Aufbau principle, Hund's rule, and the Pauli exclusion principle, ensuring that each atom has a distinct electronic configuration. This configuration is the key to understanding an element's position in the periodic table and its chemical properties. For example, elements in the same group of the periodic table have similar electron configurations in their outermost shells, leading to similar chemical behaviors. Think of the alkali metals, like sodium and potassium, all having one electron in their outermost shell, making them highly reactive and prone to forming +1 ions. Or the halogens, like fluorine and chlorine, with 7 electrons in their outer shell, seeking to gain one more to achieve stability, thus forming -1 ions. The size of an atom, its ionization energy, the energy required to remove an electron, and its electron affinity, the energy released when an electron is added, are all directly influenced by the electron's proximity to the nucleus and the shielding effect of inner electrons. These seemingly abstract concepts have tangible consequences. The way water molecules interact, leading to its unique properties like high surface tension and its ability to act as a universal solvent, is a direct result of the polar nature of the oxygen-hydrogen bonds, which in turn is determined by the unequal sharing of electrons. The formation of complex organic molecules, the very basis of life, relies on the carbon atom's ability to form stable bonds with up to 4 other atoms, a versatility stemming from its 4 valence electrons. Even the phenomenon of light absorption and emission, which allows us to see colors and is crucial for photosynthesis, is a direct consequence of electrons transitioning between different energy levels within atoms. When an electron absorbs a photon of light, it jumps to a higher energy level. When it falls back to a lower level, it emits a photon, often of a different color. This constant, intricate interplay of electrons, their energies, their positions, and their interactions, is the unseen engine driving the diversity and complexity of the material world. It is the fundamental reason why a piece of iron behaves so differently from a diamond, or why air is a gas while rock is solid. The electron's dance is the silent, ceaseless choreographer of all that we perceive as solid, liquid, and gas, of all that we interact with, and of all that makes up our very being. It is a dance of fundamental forces, of quantum probabilities, and of the relentless pursuit of stability, shaping every property, every reaction, and every facet of the material universe. The electron's subtle waltz orchestrates the very essence of matter, whispering the secrets of existence into the fabric of reality. The nucleus's enduring strength, the core of atomic existence. At the very heart of every atom, a story of immense power and stability unfolds. This is the realm of the atomic nucleus, a testament to the fundamental forces that bind matter together. Imagine a miniature solar system, but instead of planets orbiting a star, we have protons and neutrons, densely packed, locked in an embrace far stronger than any earthly force. The nucleus is incredibly small compared to the atom as a whole. If an atom were the size of a football stadium, the nucleus would be no larger than a tiny pea at its center. Yet, within this minuscule space resides almost all of the atom's mass, a concentration of energy that dictates the very identity of an element. The forces at play here are extraordinary. Protons, each carrying a positive electrical charge, would naturally repel each other with immense force, seeking to push apart. If this were the only force, atoms as we know them could not exist. But a far more powerful force, the strong nuclear force, intervenes. This force is a fundamental interaction of nature, acting over extremely short distances, and it is overwhelmingly powerful. It binds protons and neutrons together, overcoming the electrostatic repulsion between protons and creating a remarkably stable, tightly knit core. Neutrons, though electrically neutral, play a crucial role in this nuclear family. They act as a kind of glue, helping to stabilize the nucleus by adding to the attractive, strong nuclear force without contributing to the repulsive electrical force. The number of protons in a nucleus, known as the atomic number, is what defines an element. A hydrogen nucleus, for instance, has just one proton. A helium nucleus has 2. An oxygen nucleus has 8. And so on, up the periodic table, each element distinguished by the specific count of these positively charged particles. This simple number is the fundamental characteristic that determines an element's chemical behavior. However, the number of neutrons can vary within an element, leading to what we call isotopes. For example, hydrogen has isotopes like deuterium, 1 proton, 1 neutron, and tritium, 1 proton, 2 neutrons. These isotopes share the same chemical properties because the number of protons dictates their electron configuration, which in turn governs their interactions. But their nuclear stability can differ. Some isotopes are perfectly stable, their nuclei enduring for eons. Others are unstable or radioactive, meaning their nuclei will eventually undergo a transformation, releasing energy and particles as they decay into a more stable configuration. This radioactive decay is a direct consequence of the delicate balance between the strong nuclear force and the repulsive forces within the nucleus, a balance that can be tipped by the specific number of neutrons. The sheer density of the nucleus is staggering. If you could somehow take all the protons and neutrons in a nucleus and squeeze them together without any space between them, a teaspoonful of this nuclear matter would weigh billions of tons. This immense density hints at the incredible energies contained within. The strong nuclear force, responsible for holding the nucleus together, is millions of times stronger than the electromagnetic force that governs chemical bonds. It is this profound strength that makes the nucleus so enduring, so resistant to disruption. It is the bedrock upon which the entire structure of an atom is built, the anchor that gives each element its unique identity and stability. The nucleus, in its enduring strength, is the silent, powerful engine of atomic existence, a testament to the fundamental architecture of our universe. Within the nucleus's tight embrace, the universe's identity is held, a testament to forces unseen, yet eternally strong. The periodic table's grand design, a map of atomic creation. Imagine, if you will, a symphony, not of sound but of existence. A grand, ordered arrangement of the fundamental building blocks that make up everything we see, touch, and even are. This is the essence of the periodic table, a testament to the universe's patient and profound act of creation. For centuries, scientists have diligently observed, experimented, and cataloged the elements, those unique substances that cannot be broken down into simpler ones by chemical means. Each element, defined by the number of protons in its atomic nucleus, possesses a distinct identity, a unique signature etched into the very fabric of reality. The periodic table, in its elegant simplicity, organizes these elements not just by their atomic number, but also by their recurring chemical properties. This recurring pattern, this periodicity, is not a mere coincidence. It is a direct consequence of the electron configurations of the atoms, the way electrons orbit the nucleus in specific shells and subshells. As we move across a row or period of the table, electrons are added to the outermost shell, subtly altering the atom's behavior. As we move down a column or group, elements share similar outer electron arrangements, leading to strikingly similar chemical reactivity. Consider hydrogen, the simplest element with just one proton and one electron, reciting proudly at the top left. Then comes helium, with 2 protons and 2 electrons, a noble gas, content in its stable, full outer shell. Moving across, we encounter lithium, then beryllium, boron, carbon, nitrogen, oxygen, fluorine, and finally neon, each with an increasing number of protons and a corresponding increase in electrons, filling the first electron shell and then beginning to populate the second. This progression is not random. It is a visual representation of the fundamental rules governing atomic structure, rules dictated by quantum mechanics. The very columns, the groups, reveal families of elements that behave in remarkably similar ways. Alkali metals like sodium and potassium, found in the first column, excluding hydrogen, are highly reactive, readily giving up their single outer electron to form positive ions. Halogens like chlorine and bromine in the second-to-last column are equally reactive, eagerly accepting an electron to achieve a stable configuration. The noble gases in the final column are characterized by their complete outer shells, making them largely inert, aloof observers in the grand chemical dance. The periodic table, therefore, is far more than a chart. It is a predictive tool, a map of atomic creation's logic. Dmitri Mendeleev, its principal architect, famously left gaps in his table, predicting the existence and properties of elements yet to be discovered. His insights were so profound that when these elements were eventually found, they fit perfectly into his proposed structure, a powerful validation of the underlying principles of atomic organization. The table also reveals the subtle interplay between atomic size, ionization energy, and electron affinity, all dictated by the number of protons and the arrangement of electrons. Larger atoms with electrons further from the nucleus tend to lose them more easily. Elements with a strong pull on electrons, those that readily accept them, exhibit high electron affinity. These seemingly abstract concepts are the very forces that drive chemical reactions, that allow atoms to bond and form the vast diversity of molecules that constitute our world. From the simplest diatomic molecules like oxygen and nitrogen to the complex chains of DNA, all are governed by the fundamental principles encoded within the periodic table. It is a testament to the universe's inherent order, a cosmic blueprint that reveals how the raw materials forged in stars are arranged and interact, leading to the incredible complexity of the cosmos. Even the heaviest, synthetic elements, those created in laboratories, find their place within this grand design, their properties often predicted by their position, extending the table's predictive power into uncharted territories. The periodic table is, in essence, a chronicle of atomic evolution, a visual narrative of how, from the simplest hydrogen atom born in the Big Bang, through the fiery crucibles of stars, and the explosive finales of supernovae, the universe has meticulously assembled its elemental repertoire. It is a map that not only describes what exists, but also hints at what is possible, a beautiful and enduring legacy of scientific inquiry and cosmic artistry. The periodic table, a celestial cartography of existence, maps the universe's elemental story, revealing the ordered beauty of atomic creation. the universe's ongoing alchemy, the continuous cycle of atomic formation and transformation. The grand tapestry of existence, from the smallest speck of dust to the furthest reaches of the cosmos, is woven from the fundamental threads of atoms. These atomic building blocks, so seemingly stable and enduring, are in fact participants in an eternal cosmic ballet of creation and transformation. Our journey through the birth of atoms has revealed the astonishing fact that nearly every atom in our bodies, and indeed in the very fabric of our planet, was forged in the fiery hearts of stars or in the cataclysmic explosions of supernovae. But this cosmic forging is not a singular event, a one-time creation in the universe's distant past. Instead, it is a continuous, ongoing process, a perpetual alchemy that shapes and reshapes the cosmos. Consider the stars, those magnificent celestial furnaces. They are not merely passive luminaries, they are active factories of matter. Within their incredibly dense cores, lighter elements, primarily hydrogen, are relentlessly fused into heavier ones. This nuclear fusion, driven by immense gravitational pressure and searing temperatures, is the primary engine for creating elements up to iron. As stars age and evolve, they go through different stages, each contributing to the ongoing creation of specific elements. Red giants, for instance, are crucial in synthesizing elements like carbon and oxygen through the triple alpha process. As these stars swell and eventually shed their outer layers, they disperse these newly formed elements into the interstellar medium, seeding the next generation of stars and planetary systems. Then there are the dramatic finales, the supernovae. These cataclysmic explosions are not just spectacles of light and energy. They are the cosmic anvils upon which the heaviest elements are forged. In the incredibly brief, intense moments of a supernova, a flood of neutrons bombards atomic nuclei. This rapid neutron capture process, known as the R process, is responsible for creating elements like gold, platinum, and uranium. Elements that are too heavy to be formed through the slower processes within stars. The debris from these explosions, enriched with these heavy elements, is then scattered across vast distances, becoming the raw material for future cosmic structures. But the cycle doesn't end with stellar death. The dispersed elements, now part of interstellar gas clouds and nebulae, are the very ingredients for new beginnings. Gravity, the silent sculptor of the universe, draws these atoms together. As these clouds collapse, new stars are born, and around these nascent stars, protoplanetary disks begin to form. Within these disks, dust grains, themselves composed of atoms forged in previous stellar generations, begin to aggregate. This process of accretion, the slow gathering of matter, is how planets are built, atom by atom, molecule by molecule. Every planet, every moon, every asteroid is a testament to this ongoing cosmic recycling. Even after a planet forms, the transformation of atoms continues, albeit at a more subtle pace. Radioactive elements born in stellar furnaces and supernovae undergo a slow, steady decay, transforming into different elements over vast timescales. This radioactive decay is a continuous source of heat within planetary cores, driving geological processes like plate tectonics and volcanic activity. It's a constant, silent process of atomic change, a reminder that even seemingly solid ground is in a state of perpetual, slow transformation. Furthermore, the universe is bathed in cosmic rays, high-energy particles that originate from sources like supernovae and active galactic nuclei. When these cosmic rays strike the atoms in the Earth's atmosphere or on its surface, they can induce nuclear reactions, transmuting existing elements into new ones. While this process might be less significant in terms of mass creation compared to stellar fusion, it adds another layer to the intricate and ever-present atomic transformations occurring throughout the cosmos. The creation of atoms, therefore, is not a chapter closed in the universe's history. It is a living, breathing, ever-evolving narrative. From the initial moments of the Big Bang, which gave us the lightest elements, to the ongoing energetic processes within stars and the violent outbursts of supernovae, the universe is perpetually engaged in the art of atomic alchemy. It is a continuous cycle of formation, dispersal, and reformation, a grand, cosmic recycling that ensures the constant renewal and evolution of matter. This understanding offers a profound perspective. We are not merely static observers of a finished creation, but rather integral participants in a universe that is eternally in the process of becoming. The atoms that form us are ancient travelers, born in stellar hearts, scattered by cosmic explosions, and gathered to build worlds, forever cycling through the grand, ongoing alchemy of existence. Our calm exploration has covered the universe's profound journey of atomic creation, from the very first whispers of hydrogen born in the Big Bang, to the violent, alchemical furnaces of stars and the explosive artistry of supernovae. We have witnessed how nebulae serve as cosmic nurseries, how stellar winds disperse the elements, and how planetary disks gather this stardust to build the worlds we inhabit. We've traced the origins of life's essential building blocks, like carbon, oxygen, and nitrogen, and marveled at the cosmic journeys of elements like iron, gold, and uranium, forged in the most extreme events imaginable. We've touched upon the energetic dance of cosmic rays and the slow, constant transformation of radioactive decay, all contributing to the grand, ongoing alchemy of the cosmos. Tonight, we have reviewed the principles of how the very fabric of existence, the atoms that compose us and everything around us, came to be. It is a story of immense scale and intricate processes, a testament to the universe's boundless capacity for creation. Consider, for a moment, that the atoms that make up your very being were once part of distant stars, forged in fiery hearts and scattered across the cosmos. This connection, this shared cosmic ancestry, can offer a profound sense of perspective, a gentle reminder of our place within this vast, magnificent tapestry. It is a humbling and awe-inspiring thought, one that can quiet the anxieties of the day and invite a sense of deep peace. Sleep well, dear seeker of quiet wonder. It is time to rest now. If you happen to still be awake, you can drift into the next chapter now.